So restarting this, I'm going to give people another minute. Sorry, I was experiencing technical difficulties. Okay, going to give people 30 seconds and then start this again. Hopefully the internet connection's a little bit better. Okay. Okay, let's try this one more time. Okay, so chapter 28 is the last chapter we're covering. I'm going to do about half of it today, half of it on Thursday. And just as a little recap, anytime a wave hits a surface, so it could be a sound wave, could be a light wave, three possibilities for what's going to happen. One, that wave can get absorbed. Two, that wave can get reflected. Three, that wave can get transmitted through. And in chapter 26, we talked a little bit about how light gets through a transparent material. So just as a reminder, let's say this is a piece of glass, and I've got a bunch of little atoms inside the glass. In reality, there's an insane number, billions and billions and billions. I just drew a few. Remember, what happens is this light wave comes in, it gets absorbed by this very first atom in the glass. An electron in that atom will absorb that light. That light completely disappears. The energy the light had got transferred to the electron. Electron oscillates up and down, emits a new piece of light that then goes on to the next atom, gets absorbed, so on and so forth. One thing I didn't go through is that when light goes through a transparent material, such as glass or air to water or something like that, oftentimes that light will bend. And that's the subject of the last part of this chapter called refraction. Now, when light gets reflected, remember what happens is if the frequency of this light matches one of the natural frequencies of the glass, that light is going to get absorbed. But if the frequency of the light does not match one of the natural frequencies of the glass, that light will then either be reflected back towards the observer or transmitted through, or both. And in fact, oftentimes all three are happening. So for example, light hits glass, that glass can absorb some of the light, that glass can reflect some of the light back, and that glass can transmit some of the light through. So what we're going to deal with at the beginning is reflection. Let me make this a little bit bigger. So one very simple law called the law of reflection. And it says this: anytime light hits a surface, the angle that it hits at and the angle that it reflects at are the same. So one, the angle it hits at, we call the angle of incidence. The angle it reflects at, we call the angle of reflection. And one of the big things in optics is angles are always measured with respect to something called the normal. And the normal is a perpendicular line drawn at the point where the light hits that's perpendicular to the surface. So for example, if this is an incoming ray of light, and I want to know how is that light going to reflect? Well, the angle I care about is the angle between the normal and the surface. So in this case, the normal, I would draw a perpendicular line. The angle that it hits at is this angle here, and that's called the angle of incidence. The angle that it reflects at, again, I would measure that angle with respect to what's called the normal. So this little line drawn perpendicular, the angle it reflects at is called the angle of reflection. Those two angles are always, always, always equal to each other. So let me just show you a little share here. Reflection model. Okay, so we're going to talk about mirrors in a second, but here is the normal. So I have a beam of light that's hitting a surface. In this case, it could be a mirror. If I want to know how is that light going to reflect, then what I'm looking at is what's called the angle with respect to the normal. So this, can I draw on this? I can't draw on this, but this angle right here between the normal and the incoming light, that's the angle of incidence. This angle right here, the angle between the normal and the outgoing light, the reflected light, that's the angle of reflection. And let's see if I can put these hide angles. Let's show angles. Okay. Okay. So you don't need to know like the angles, but the angle between this incoming ray of light and the normal is 35.4 degrees right now, which means the reflected light is going to reflect off the surface at the exact same angle. If I change the angle, so like, can I move my eye? Ooh, I can move the eye. So like right now, the angle between the incoming light and the normal, 50.5 degrees, that's going to be the exact same angle that it reflects at. So let me go back to this. Whoops, new share. I want to go back to, let me just do PowerPoint for a second. Okay, so here you can see it another way. So law of reflection just says this: whatever angle light is hitting at, which we call the angle of incidence, that's going to be exactly the same as the angle that it reflects at. Simple law called the law of reflection. And if you've ever played pool and you want to do a bank shot, this is basically how you figure out the angle that you were hit at. So, you know, let's say I've got a pool ball and I want this ball to, you know, come somewhere over here. What I'm doing is figuring out the angle that it hits at so that the angle that it reflects at is exactly the same. And the angles I would care about are always the angles measured with respect to the normal. And that's just a line that you draw that's perpendicular to the surface at the point where it hits. So I'll talk a little bit about how do we actually see with mirrors, because it's pretty cool. So one, your brain, hold on for a second, let me just mute people, chat. Hold on one second, stop. Mute participants upon entry, continue. Okay, let's go back to this share, screen share. So I want to talk a little bit about how we see images in mirrors. And one important point I want to make, just to begin with, is your brain cannot tell the difference between reflected light and light coming from an actual source. Meaning, let's say that I am over here somewhere. Here's my eye. Wow, that's a horrible eye. Let's do a better eye. So I'm over here somewhere, and I see these light rays coming off the mirror. And you know, there's all these other rays, but let's say I'm over here, and I can see this light ray coming off the mirror. Well, to me, it looks as if it was coming from an object behind the mirror that was really emitting light. And our brain cannot tell the difference between an object which is really emitting its own light and an object that's light reflects off a mirror and then comes to us. So if I'm over here and I see these light rays coming off the mirror, to me, it looks exactly the same as if there wasn't a mirror here at all, but there was really an object behind the mirror producing light. So, well, let me go back to the lecture notes. So there's a difference between what we call a virtual image and a real image. A real image is the only kind of image that you could actually project onto a piece of paper, but the image is from a plane mirror, the kind of mirror that you're used to looking at in your bathroom or something like that, or what's called a virtual image. And the reason it's called a virtual image is The light rays are not actually coming from an object behind the mirror. They just appear to. So this object is emitting light in all different directions. We're only looking at a few pieces of it. Your brain always assumes light traveled in a straight line. Your brain doesn't know that light bends. Your brain doesn't know that light reflects. It always assumes it comes in a straight line. So if I was over here looking and I saw these two rays of light coming, what your brain does without you even thinking about it, if you've taken math, it does a linear extrapolation. It sees these light rays, and in essence, your brain traces them back and looks to see where it looks like they came from. That's where your brain will actually see the image. So we see all these light rays coming off a mirror that got reflected. Your brain basically is like, okay, these light rays coming off must have come from an object right over here. This is where your brain sees the image. Kind of cool. In a sense, a virtual image only exists in your brain. You could never actually project that image onto a piece of paper and get a clear image. So, plane mirrors, a couple things about them. One, the image and the object always have the same size, meaning your image always appears to be the same size as you. And another interesting thing is the image is always as far behind the mirror as the object is in front of it. And as I'm kind of saying, your brain can't tell the difference between an object and its reflected image, meaning reflected light from an object enters the eye in exactly the same way as if there really was an object behind the mirror at the image location. I'm not quite sure the best way to sort of make that clear, but imagine I had a light bulb right here, and that light bulb is emitting light in all different directions. We're only considering some of the light rays. Every one of these light rays that hit, let me change this color, draw, let's do blue. Every one of these light rays that hit obeys the law of reflection. So if I look at this one light ray right here, I would draw a normal. The angle that it hits at and the angle that it reflects at are the same. Now your eye is going to see a bunch of these light rays that get reflected off of the mirror. What your brain does, like I said, is it takes these light rays, and without you even thinking about it, it does, in a sense, a little mathematical operation. It's like, where did these light rays originate from? And what your brain does is it places the image where you see the object, or the image is where these light rays appear to have originated from. So all of these light rays bouncing off the mirror look exactly the same as if there wasn't a mirror there at all, but there is an object here emitting light. That's where your brain will see the image. You could do some math and show that if you are a certain distance in front of the mirror, then your image will appear to be that exact same distance behind the mirror. So if you're standing 2 feet in front of a plane mirror, your image in the mirror will look like it's 2 feet behind the mirror. Let's not talk about that part. So, pretty interesting again. Your brain does not know that light bends. Your brain always, always, always assumes that light travels in a straight line, and it basically projects that line back, and where it looks like that light originated from is where you see the image. And just as an interesting point, I don't know if you've ever heard of gravitational lensing, but about, I don't know how long ago, 20 or 30 years ago, astronomers saw 2 identical galaxies in space that were identical in every way. So let's say I saw a galaxy here, and I can't draw, so the galaxies are just, so here's the Earth. And what ended up happening was we saw 2 identical galaxies, like identical in every single way, right next to each other in space. And people were completely blown away. How could I have 2 identical galaxies? Well, what they figured out was, let me erase this. Here's a galaxy. Let's say here's the Earth, and here is a massive black hole. we didn't really talk too much about black holes, but a black hole is a star, a massive, massive, massive star that's basically run out of nuclear fuel. Gravity's taken over, the star collapses down to an infinitely dense point, so dense that not even light can escape, which is why we call it a black hole. But one of the things about black holes, let me move this a little bit, is they can actually bend light. So what we finally figured out is this galaxy way far away, there's a, let me move this a little bit. There's a supermassive black hole between the galaxy and the Earth. This galaxy is emitting light in all directions. So some of that light is traveling straight to the Earth. So we always assume light traveled in a straight line, so we'd see the galaxy where it is. But what also happens is this galaxy is emitting light in all different directions, but some of that light passes close enough to the black hole that it gets bent. Our brain, all optical instruments like cameras and things like that, always assume light traveled in a straight line. So we see this beam of light. To us, it looks like it's coming from a galaxy along a straight line path. So what we ended up figuring out is these two identical galaxies that we saw was really one galaxy emitting light in all directions. Some of that light was passing straight to the Earth, not moving close enough to the black hole to get bent. But some of that light was passing near a black hole, getting bent, and then whenever we see light, we always assume it traveled in a straight line. So this second galaxy that we saw, and not just saw, we took a picture of it with the Hubble telescope. That second galaxy was really light that passed close enough to a black hole that it got bent. And again, your brain doesn't know that light bends, and so it just assumes it moved in a straight line. So we ended up seeing two galaxies. Let me stop this for a second and just open it up for questions. Oh, we're not even recapping anymore. So light hits a surface and it reflects. The angle that it reflects at is the same as the angle that it hits at, but we always measure angles with respect to something called the normal, which is a line drawn perpendicular to the surface at the point where the light hits. Your brain doesn't know that light reflects. Your brain doesn't know that light bends. It always assumes light travels in a straight line. Where you see the image of an object is where that reflected light looks like it originated from, and that's where your brain tends to see the image. Let me just pause for a second. What questions can I answer just about that beginning concept of light reflecting off a surface, your brain sort of extrapolating the light, seeing where it looks like it came from? Questions? If not, gonna move on. Okay, let's go back to the screen share. PowerPoint, onto PowerPoint. Okay, so again, just one more time. An object. So one, we're considering something right here. It could be a light bulb, it could be something. It's really emitting light in all directions. We're just looking at the light that reflects off the mirror. So I've got all these little light rays hitting. Every one reflects off the mirror and obeys the law of reflection. Angle of reflection equals the angle of incidence. You then see these reflected light rays coming from the mirror. Your brain doesn't know it reflects, and so what it does without you even thinking about it is it traces all these light rays back to see where it looks like they came from. That's where you will see the image in your brain. We call it a virtual image because I cannot project that image onto a piece of paper. So in a sense, that only exists in your brain, which is kind of a cool concept. Couple things about the plane mirrors. Your image is always as far behind the mirror as you are in front of the mirror. Okay, that's all I want to talk about for that. Not going to talk about curved mirrors, but there's two other kinds of mirrors that generally you'll see. One of them is called a concave mirror, and the other one's called a convex mirror. But I don't have these mirrors with me. I can't really show you any demos, so do not worry at all about curved mirrors. Okay, talk a little bit about two different kinds of reflection. So we generally classify reflection into one of two kinds. First kind is called specular. Second kind is called diffuse. So specular is not good reflection for seeing. So reflection from a smooth surface is what we would call specular reflection. So I have a 100% smooth surface. Light hitting it is all going to sort of reflect in the same direction. Now, the reason that's bad is because if I had a 100% completely smooth surface, let's say that I was over here trying to see something. Well, if all of that light is reflecting off this surface in the same direction, none of that light would enter my eye. I wouldn't actually see the object. So if surfaces were 100% completely smooth, most of the light hitting it would all reflect in the same direction, which means if your eye wasn't right over here, you wouldn't see that object at all. Well, luckily, at the atomic level, no surface is completely smooth. If I were to look at the atomic level, the surfaces are very rough. Now, these are little bumps that are at the atomic level, meaning they may only be 10 or 15 atoms high. But here's the thing. If the surface is not smooth, then when light is hitting it, so I've got all these light rays coming in, they are not all going to reflect in the same direction. And the reason is, when you look at reflection, the angles are always measured with respect to the normal, which is a line drawn perpendicular to the surface. And if I have a bumpy surface, the normal is going to point in all different directions. And because of that, it's going to get reflected in many directions, and that's called diffuse reflection. And this is actually a really good thing. Most of the things that we see every single day are because of what's called diffuse reflection. So for example, here's the same light that was coming in. It was hitting a smooth surface, and all of that light was getting reflected in the same direction. But if the surface is not smooth, then I still have the law of reflection holding, but it's going to reflect at different angles because it hits at different angles. Going back here, if I zoom in for a second, every one of these, if I want to know how the light reflects, I have to draw a normal, and the angle that it hits at and the angle that it reflects at is the same. And the normal for every one of these is along the same direction because it's completely smooth. Well, if I look at this one, the law of reflection still holds. And if this is drawn well, then if I want to know how is this particular beam of light going to reflect, I would have to draw a normal at the point where it hits. And if I drew this right, then this angle here and the angle that it reflects at are the same. And again, here, the normal is always perpendicular to the surface. So the normal for this light ray would point like that. And so the nice thing about this is, let's say that this was a piece of paper that you're reading. I could be right here, and I would see the piece of paper. I could be right here, and I would see the piece of paper. I could be right here, and I would see the piece of paper. Whereas if I had specular reflection, my eye would have to be right here in order to see that piece of paper at all. If I was in a different location, then I would not be able to see it. So because of diffuse reflection, we can pretty much see objects from any direction or any position, and almost everything we see is because of diffuse reflection. So I want to ask you a kind of cool clicker question to think about. Thinking about all of that, this is clicker question 28.3. Says the following: which kind of road surface is it easier to see when driving at night? A pebbled uneven surface or a mirror smooth surface? So you're driving at night and the road could either be pebbled and uneven or mirror smooth. What kind of surface would it be easier to see that? And let me see if we can do this as a poll. Launch polling. All right. If you're on a computer, I've launched a poll, completely anonymous. What do you think? You're driving at night What kind of surface would it be easier to see on, a pebbled uneven surface or a mirror smooth surface? So far, we've got 100% say A. Wouldn't it be crazy if 100% of you were wrong? All right, I'm going to stop this. Share results. Everybody says a pebbled uneven surface. And the answer is A.
Drum rolls, please.
Drum roll, please. The answer is A. And let me kind of show you a little picture of why. And let's draw view. Let's do some line rules here. Okay, so let's say that here's the road. Here's the car. Here's you. Here's the headlights. So one thing to keep in mind that you may never thought of before, if you're driving at night and you're going to see the road, that means light from your headlights have to reflect off the road and then come back to your eyes. So if the surface of the road was 100% completely smooth, so you've got your headlights that is hitting light in all directions. Well, what's going to happen is any light that hits the road, all of it is going to get reflected forwards. You're not going to see any of that light. So if the road was 100% completely smooth, all of the light from your headlights would reflect forward. None of it would reflect back to you. What really happens is, let's draw the same situation. At the atomic level, and I'm going to, draw this a little bumpier than it is. No surface is completely smooth. So what ends up happening is your headlights are emitting all this light, but because the road is bumpy, some of that light can actually reflect back to you. Some of that light's going to reflect forwards, but if the road is bumpy, then some of that light gets reflected in all different directions. So you've got all these rays hitting, some are going to reflect up, some's going to reflect forward, but some of it will reflect back towards the driver. The only way that you can see the road is if light from your headlights hit the road and then reflect back towards your eyes. So I think one of your homework questions is, why is it more difficult to see the road on a rainy night? What is your homework question? Hold on one second. Physics 10. Homework assignments, chapter 28. Why is it difficult to see the roadway in front of you when driving on a rainy night? So what happens here is, again, let's sort of overemphasize this. So let's say here's the road. And you're driving on this bumpy road. You've got your Canyonero. Canyonero. What ends up happening is, when it's raining out, the water, in a sense, fills in all the little gaps on the road. So this is going to be green rain. So the water fills in all the gaps, making it, in a sense, more like a mirror, making it more mirror smooth. When that happens, all the light from your headlights now reflects forward because I have, in a sense, a flat surface that the light is reflecting off of. So this happens, this also explains why if you're driving at night and you're passing somebody, you can get a tremendous amount of glare. So let's say that you're driving in the other direction. Well, maybe on a different road, but you're going to head-on collision. So the rain fills in all the little gaps of the road, making it more like a mirror. All of the light gets reflected forward. So this driver here is not going to see the road at all. Pretty interesting. They would actually see nothing if none of that light is getting back to them. But as this car is passing by, at one point it's going to hit a part where all of the light reflecting off the road reflects to them. You're going to see a tremendous amount of glare. Okay, let me stop that. Just open it up again. for any questions before I just touch on refraction. So light always reflects when it hits a surface, most of it. Angle of incidence equals the angle of reflection. Angles are always measured with respect to the normal, and our brain always assumes light traveled in a straight line and basically traces the light back to see where it looks like that light originated from. That's where we see the image of from a mirror. Okay, what I want to do is just spend about 10 minutes introducing refraction, and then we'll finish it up on Thursday. And let me start with a screen share of bending light intro. Okay, so I mentioned that. Let's turn this on. Whenever light hits a material, some of that light can get absorbed, some of that light can get reflected, some of that light can get transmitted through. The reflected light obeys the law of reflection. So this angle here is the angle of incidence. This angle here is the angle of reflection. Let me make this material a little bit bigger. The one thing we didn't go through before is that when light is transmitted through material, like from air to glass, from glass to air, or from air to water, that light can bend. And we call the bending of light as it passes from one transparent material to another, refraction. And anybody who wears glasses, contact lenses, or anything like that, refraction is pretty much responsible for letting you see clearly. So you got light ray coming in, hits a surface. It's possible some of that light is going to get absorbed. If it's absorbed, then the water in this case, or the glass, would heat up a little bit. Some of that light is going to get reflected. Angle of reflection equals angle of incidence, but some of that light that passes through is going to get bent. We call the bending of light refraction. So going to the lecture notes. Let me just skip by this. So one, just real quick, here's a just bigger view of it. Specular reflection is reflection from a smooth surface, which isn't ideal because if our eye was here, we'd be able to see it. But if I was over here or something like that, I'm not going to be able to see it. Most material, however, is not smooth at the atomic level, it's rough. And because of that, the light reflects in all different directions, so I can see this object pretty much no matter where I am. Okay, so here's a great little example of refraction. So this is just a beam of light coming in, kind of hard to see, but there is the little bit of light that does get reflected here. But this is, you can see, is the light that gets transmitted through. And it's bending because if it was traveling just in a straight line, the light would have went something like this. But as it went from air to water, that light bent, and the bending of light as it passes from one transparent material to another is what we call refraction. Now, here's a great way. I love the way your book does this, and I actually use this in my calculus-based physics classes too. And this is how to tell which direction light is going to bend. And the way you understand it is by imagining a cartwheel which is rolling. And let's say it's rolling from the sidewalk onto grass. So in the sidewalk, it's moving faster. And in the grass, let's just say it moves slower. Well, you could also imagine, let's say you probably have had this experience, you have a shopping cart and one of the wheels in the shopping cart doesn't roll well. Well, what always happens is, let's say I push the shopping cart and one of the wheels isn't rolling as fast, it's going to turn and it's always going to pivot about the wheel that's not rolling as fast. Well, here, imagine I had just these two wheels, cartwheels, and they are rolling and they go from the sidewalk to the grass. Well, if the wheels don't hit at the same time, so one wheel hits the grass before the other wheel, then what's going to happen is that wheel is going to slow down, assuming that it rolls faster in sidewalk than it does in the grass, while the other wheel is still moving the same speed it was before. So you imagine this cartwheel, this wheel is going to hit the grass first and slow down, where this wheel is still in the sidewalk, so it's still moving at the same speed it had before. Well, if this wheel keeps moving the same speed and this one slows down, it's going to cause it to turn. So the wheel that slows down first is going to cause this cartwheel to change directions. And that's pretty much the way that you can imagine why light is bending. It's when one part of the light hits a different material first, where the speed is not the same. So similarly, when light hits a transparent material where the speed of light is slower, so let's say water, one side is going to slow down before the other. So we'll talk about this a little bit probably on Thursday, but how fast light travels through material depends upon how many times it has to get absorbed and re-emitted, absorbed and re-emitted. So something like water, which is a lot more dense than air, light travels slower in water than it does in air. So if I had a ray of light, I would imagine these little cartwheels sort of. And if I imagine that this side of the cartwheel is going to slow down first, while this other side is still moving faster, that's going to cause the light to bend the same way it would cause cartwheels to bend. So in this case, the left side of the wavefront slows down first, causing it to bend. And I have a little animation to show you dealing with that. Can I do that? Oh, no, hold on, animations, refraction. Will you open up? Allow blocked content. Okay. New share. So here's an example of refraction happening. So I think this will reset in a second and you can see it. But if you imagine cartwheels, so this could be a cartwheel. This is somewhere where the speed of the light, or in this case, the speed of this roll. Can I reset this? Let me try this one more time to reset it. Okay, so coming in, when one side slows down before the other, that's going to cause, we're talking about cartwheels, them to pivot around the slower wheel. And the opposite is happening as we're leaving. So if I imagine in here, the speed is slower, out here, the speed is faster. As this side hits the faster area, it's going to speed up. And again, I'm going to pivot around the slower wheel or the slower side. So you imagine light coming in, this side slows down first while this one is still in the air moving faster, causing it to pivot. And then this side hits the air where it's moving faster, causing it to pivot again. So thinking about which side is going to slow down before the other will let you think about how is light going to bend. All right, let's go back to this again, PowerPoint. Oh, I kind of showed you the answers. Are those the answers? Oh, I wanted to do that without the answers. Okay, anyway, I was going to have you do a little question here, but you can see the answers, but let's do it together. This is exercise 20. So a pair of toy cartwheels are rolled obliquely from a smooth surface onto two plots of grass. A rectangular plot and a triangular plot is shown. The ground is on a slight incline, so after slowing down in the grass, the wheels will speed up again when emerging on the smooth surface. Finish each sketch by showing the path the cartwheels take inside the grass and on the other side. So just real quick, let's just look at this first one. So in this case, I've got the cartwheels coming in. Here's sort of the beam the light's taking. Oh, I'm gonna have to move this a little bit. Let's move that up here. As this is going, what's gonna happen is this wheel, I'll just do that over here. This bottom wheel is going to hit the grass first, causing it to slow down, which means that this wheel is gonna slow down first. This wheel is still gonna be moving faster. It's gonna cause this thing to pivot. Now, one thing that you can't tell is how much it's going to bend. You can only tell the direction it's going to bend. Mathematically, you could solve an equation called Snell's law to figure out exactly how much it bends. You don't need to worry about that. Here, I don't like this drawing. This makes it look like these are hitting at the same time. So this part here, I don't think is correct. But the one with the triangle is definitely a little bit more easy to see. So here I've got this cartwheel. And what's going to happen is this bottom wheel is going to hit the grass first. The top wheel is still in the, what is this, cement or whatever, still going faster. So once that happens, this light coming in, this first cartwheel hits, what's going to cause it to pivot around the slower wheel. And now if I look at this part, now what's going to happen is this top wheel is going to hit the part where it's moving faster while the bottom wheel is still inside, and it's going to cause it to pivot again. And just as a little preview, the way prisms work is just, it's a triangle of light, or not triangle of light, it's a triangle of glass. Light comes in, and what ends up happening for a prism is usually this incoming light is white light. And then what we're going to see is different frequencies of light actually travel at different speeds in glass. Blue light travels at a slightly different speed than red light, which travels at a slightly different speed than green light. How much light bends depends upon the speed of light in the material. So white light passing through a prism, the red part of white light is going to get bent by a different amount than blue, and so on. So just as a little preview, oh, actually, before I do that, there's one other cool thing that I want to just touch on, and then we'll just finish with this. Because of refraction, remember, your brain always assumes light traveled in a straight line. But whenever light goes from one transparent material to another, it bends. Well, your brain doesn't know it bends. Your brain assumes it traveled in a straight line. So because of that, objects in water are always, always, always deeper than they appear. So here's a chest, and the chest is not emitting its own light, but there's some sunlight that gets through the water, hits the chest, and some of it's getting reflected. And we're just looking at two rays of light here, these two. Well, once these rays go from water to air, they're going to bend in this direction. So you see these two light rays right here, and to your brain, what it does is it says, oh, well, it looks like these light rays originated from an object at this position here. That's where your brain is going to see the object. So anytime you see an object in water, it's always deeper down than it appears, because the light that comes from the water to the air bends. Your brain doesn't know it bends, and so it always assumes it traveled in a straight line. I don't know how well you can see this, but this is why if you have like a pencil or ruler or something and a thing of water, it looks like it bends. And that's because, like, here's the, let's say, end of the ruler. I've got some light coming up, but once it goes from water to air, it bends. Well, again, your brain doesn't know it bends, so if it sees these two light rays, to you, it looks like it came from right here. So a little interesting point about this, and this could one day save your life. And I actually was hoping to use this on Survivor if I ever got on it. But here's the last thing we're going to do today is this question. Question 28.5. And it says, if while standing on a bank you wish to spear a fish in front of you, would you aim above, below, or directly at the observed fish to make a direct hit? If instead you zap the fish with a laser, would you aim above, below, or directly at the observed fish? So for this, so here you are, and here's a little blinky fish here. You got two possibilities. You're either going to throw a spear at Blinky, or you're going to shoot him with the laser beam. The question is, if you're going to spear him, would you aim above, below, or directly at the fish that you see? If you were going to zap him with the laser beam, would you aim above, below, or directly at? And let's do this just as a poll. So if you have a computer, I just opened up a poll. What do you think? If I'm going to throw a laser at, or throw a laser, I'm going to throw a spear at the fish. Would I aim above, below, or directly at? If I'm going to shoot it with a laser beam, would I aim above, below, or directly at? What do you think? Give people about 20 seconds if you want to throw in a vote. And again, if you're ever trapped on a deserted island, this could one day save your life. Believe it or not, it saved mine a couple times. Not really. Okay, let's just end this polling.
I wasn't able to see the screen.
Oh, can you guys see the screen right now?
I was just, it's just I'm on my phone, so like when the poll came up, it took up the screen, so I couldn't see the.
Okay, yeah, don't worry about. I'm not tallying these votes or anything like that.
For sure.
All right. So with the results, we've got a slight majority say B, above, directly at. So would you aim above, below, or directly at? So let's look at this. And I'm just going to draw one ray of light. I'll draw a couple. So one, the light from the fish is reflected light. Well, there are some bioluminescent fish, but most fish are not emitting their own light. So I've got sunlight coming through the water, reflecting off the fish. If I'm going to see the fish, then the light has to basically hit my eye. So what happens is, as light is going from water to air, it bends. And your brain always assumes light travels in a straight line. So you're going to see the fish here, when in reality, the fish is here. You always see the fish higher than it really is. Objects are always deeper than they appear to be. So if you were to aim directly at the fish with a spear, you would miss it. So you definitely always want to aim below where you see the fish if you're going to try and throw a spear at it. Now, the interesting thing about light is light will bend the same way. It'll take sort of the same path. So the light going from water to air will behave exactly the opposite of light going from air to water, meaning light going from air to water will bend in this exact same way. And so if I were to shoot the fish where I see the fish with a laser beam, so I see the fish here and I shoot it with a laser beam, then once that laser beam hits the water, it's going to bend sort of in the opposite way it was bending in going from water to air. So if I shoot the fish with the laser beam and I point the laser beam where I see the fish, it will hit it because it'll bend in the opposite way. So the correct answer was, you want to aim, would you aim above, below? You'd aim below and directly at. So the correct answer is E. Now, if you want to get technical, I'm not going to test you on this, but depending upon the color of the fish and the color of the laser beam, you would have to take that into account. Meaning, if the fish was blue and you were shooting it with a red laser beam, the blue light would bend a slightly different amount than the red light, and so you would have to take that into account. But ignoring all that, objects in water are always deeper than they appear. So if you were going to go spear fishing and throw it at where you see the fish, you're going to be aiming above where the fish really is. However, if you were to shoot it with a laser beam, that laser beam would bend in going from air to water, and pretty much the opposite way it bends in going from water to air. And so you would still make a direct hit. Ha, booyah. Okay, so that is it for chapter 28, part 1. Just a quick little preview of what we're going to cover on Thursday, real quick. What's left is I'm going to talk about a couple cool things. One, we're going to talk about mirages. What is a mirage? And the fact that we actually see the sun after it's already set, which is a very cool concept. Our atmosphere bends light, and because of that, we see the sun after it's already set below our line of sight. And then we're going to talk about dispersion in rainbows. Very cool little concept. Nobody has ever seen the same rainbow that you have. Every time we see a rainbow, it's just for you. No two people have ever seen the same rainbow ever. Kind of a cool concept. And then the last thing we're going to talk about is just something called total internal reflection. So on Thursday, I'll finish up the chapter. And what I'll probably do is I'll have a little bit of time left over. I'll go through the chapter 28 homework, and then we're done. So thank you, everybody that joined me live. I'm taking out the lecture portion of this Zoom, bringing in office hours. If anybody has any questions about anything I've covered in chapter 28, let me know. If not, I'll hang out here for about 15 minutes, see if anybody has any questions. Thank you, everybody who joined me live. Hope you have a wonderful day today. Thank you, everybody. Hey, Allie, do you have any questions for me? There's no questions. I'm just going to pause this video and stop recording for a while. Nope. All right. I think we are done.